Hey everyone, Brian here. So today we're going to be discussing thermochemistry and thermodynamics as applied to the AP Chemistry exam. Here's an overview of the list of topics. As you see, there's a big change in styling moving forward with the videos. Let me know if you guys do find this a bit better or you prefer the previous style, and give a thumbs up if you find the content useful. That being said, let's get started. So first we're going to be talking about heat, kinetic energy, and temperature. Let's start off by defining each of them. We have heat, kinetic energy, and temperature. When we say heat, what exactly are we referring to? Heat refers to this idea of energy flow. Imagine I have a container and then a separate container right next to it. Heat would be energy flowing from this container over to this one. We know things tend to flow from a higher energy state down to a lower energy state. Kinetic energy refers to the energy due to motion. We covered it in the last section where we know the formula for kinetic energy is 1/2 mv squared. Typically that m refers to the molar mass of any given molecule, velocity, the speed of the molecule, and this analyzes only one specific molecule. If we want to look at an entire sample, we look at temperature, which is defined as the average kinetic energy. Let's take a look at the second at the units here. Heat, we normally talk in joules per mole or kilojoules per mole, same thing, just different magnitude. Kinetic energy is going to be in joules or kilojoules, and then temperature will typically be measured in Kelvin. Now, for the savvy amongst you, you might have noticed that temperature is defined as average kinetic energy, whereas kinetic energy is energy due to motion, but there's a clear mismatch in the units. So there's a little bit more with regards to temperature. The main difference between temperature and kinetic energy is that temperature incorporates this thing called degrees of freedom. That is, however, outside of the scope of this class. If you are interested in that, I'll put an article in the description below to describe that a bit more, but as far as this class goes, you don't need to worry about that. Heat, then, this idea of energy flow, we define as delta H, so it might change in enthalpy. Kinetic energy, then, just movement due to motion, and temperature always in Kelvin. So, what is a state function? A state function is one that is concerned primarily with change denoted with that delta sign. So we do not care about where we start and where we end. We are only concerned with the difference between these. So the change in value of your starting point and your ending point. State functions were always denoted with that delta sign at the beginning, and we have three main state functions that we're going to be working with in this section. The first is delta H, which is your changes in enthalpy. The second is delta S, changes in entropy, and the third, delta G, changes in Gibbs free energy. Sometimes you may see a little circle here on the top right. That little circle refers to standard state conditions. Standard state conditions are 1 atmosphere, having every compound there at 1 atmosphere. You have pure liquids, pure solids. You're going to have 1 molar concentrations. Temperature is going to be 298 degrees Kelvin, etc., etc. So it's just a set of standard conditions that are required or that are enforced when you have this little circle. As far as questions are concerned and whether or not your math is going to change or any of that kind of stuff, it doesn't really matter. So if the problem does give it to you with a little circle, keep it throughout. If not, then don't bother. Moving forward, let's talk about enthalpy a bit more. So we know enthalpy is seen as follows. And this refers specifically to the change in enthalpy. But what is enthalpy itself? enthalpy, we can see it's synonymous with heat flow per mole of reaction. And this part is very, very important. So for starters, let's say we have a simple equation where A plus B gives you C, and we're told that the change in enthalpy is going to be negative 10 kilojoules per mole of reaction. This idea of a mole of reaction actually has nothing to do with the typical definition we use for a mole, so 6.02 times 10 to the 23rd, whatever. A mole of reaction you can think as one round of this whole experiment, this whole procedure or reaction or whatever it is that we're talking about. So when we have 1 mole of A reacting with 1 mole of B to form 1 mole of C, this whole thing is known as 1 mole of reaction. So 1 mole of reaction by definition will have 1 mole of A, 1 mole of B reacting to form 1 mole of C. If the equation was written out slightly differently, so in this case I would have 1 mole of A, 2 moles of B reacting to form 1 mole of C. Now 1 mole of reaction would be defined as the one that uses 1 mole of A, 2 moles of B to make 1 mole of C. This enthalpy value is always then defined in terms of moles of reaction. So if I have this reaction and I were to proceed through 1 round of it, what is my energy release or energy absorbed? Here we see a negative value. So what exactly does that mean? A negative value refers to a release of energy, and a positive value refers to energy being absorbed. When energy is released, things get physically hotter. If you put a thermometer next to some reaction that has a negative change in enthalpy, that value in the thermometer is going to go up. When energy is absorbed, things get colder. In that case, the reading on the thermometer would go down. We can describe this a bit more using exothermic and endothermic reaction diagrams. So what does it mean for a reaction to be exothermic? A reaction is exothermic when it has a negative change in enthalpy, and it will be endothermic when we have a positive change in enthalpy. Exothermic reactions increase my temperature, and endothermic reactions decrease my temperature. You should have seen diagrams by now that look as follows, and this shows a reaction proceeding over the course of time. So here we're going to have time, and here we're going to have energy. I start out at a certain value for energy. I need to input a bit of energy into the system for it to react, and then here at the bottom is that final state in energy. Your change in enthalpy on these diagrams are always going to be this region. Because I dropped, my final stage is lower than my initial stage, this will have a negative change in enthalpy. So this graph follows one of an exothermic reaction. On the other hand, if we were to have a graph that starts here, increases, and then his final state of energy is higher than the initial one, delta H is now going to be this change. In which case, the products minus reactants, so that final stage of energy minus my initial stage of energy is higher, my change in enthalpy was positive, this would be endothermic. Now the other thing that we can see here are these bumps. What exactly does that mean? Those bumps correspond to your activation energy. From here to here is the energy needed to start that reaction. And the same thing on this side. And you've heard of these things called catalysts by now. So catalysts They show up in a bunch of different topics. We're going to start introducing them here. We're going to see a bit more later on kinetics and equilibrium, what catalysts do, but this is a good introduction to them. Catalysts will always speed up a reaction by lowering the activation energy. So you can imagine that we can depict the presence of a catalyst in this case by doing this. Now that this value has dropped, my new activation energy would only be here. So that red line would be the same graph, but with a catalyst. More on that in the coming sections. Moving on. How do we actually calculate your change in enthalpy? There's three things we can do. First, we can use enthalpies of formation. Second, we can use bond energies. And third, we can use Hess's law. Of these three, the idea represented here is going to be the one that most commonly shows up, because the same idea for enthalpies of formation applies to entropy and it applies to Gibbs free energy. So let's talk about that one a bit more in depth. So delta H for enthalpies of formation. Again, it will be denoted as follows. Your formula for this is going to be the sum of all my enthalpies of formation in the products minus the sum of all my enthalpies of formation in the reactants. So effectively, products minus reactants. But what exactly does that mean? What's an enthalpy of formation? An enthalpy of formation is the energy value assigned when you take constituent elements in their very, very basic naturally occurring form. You can think about things like sodium on its own, chlorine on its own. Well, chlorine's atomic, so it would be CO2. You would have N2, O2, H2, etc., etc., etc. All of these things in their naturally occurring versions. To take that and to bring it into whatever compound it forms in. Let's say in the case of water, for instance, it would be the energy required to take a bunch of H2 and a bunch of O2 to eventually make water. If you want to balance it out, it'd be as such. How do you find the actual values for enthalpies of formation then? Let's use this exact same example then to calculate the enthalpy of formation for the reaction that creates water. When you're asked these kinds of questions, you're going to be given a table with all the molecules that are given to you and their enthalpies of formation. The enthalpy of formation for water is negative 242 kilojoules per mole, O2 and H2. We mentioned earlier that those are the naturally occurring versions of that specific element. So they are going to have values of 0. Everything that occurs naturally will have an enthalpy of formation of 0. So how do we apply this equation? Products minus reactants. What are my products? I have water molecules and I have 2 of them. So it will be 2 times negative 242 minus what's in my reactants. In my reactants, I have 2 waters, so 2 times 0, plus 1 oxygen, 0. This whole thing obviously ends up being 0, and then your final answer is just negative 484 kilojoules per mole. And this would be the change in enthalpy found using enthalpies of formation for this specific question. You can do the same thing now using bond energies. So what's a bond energy? A bond energy is the energy needed to break a bond. Let's talk about that for a second, because this idea of breaking bonds and forming bonds are polar opposites, and sometimes it can be a bit misleading. The easier one to define, in my opinion, is breaking a bond. Imagine I have a stick. We're holding a stick in both of our hands. I want to break this stick. How do we break this stick then? We have to physically put energy into this system in order for that to happen. If the process of breaking this requires an input of energy, then that process is one that has a delta H value, which is positive. It's endothermic. Breaking bonds is always going to be an endothermic process. It requires energy. The opposite then, forming a bond, will be an exothermic process. Breaking bonds always requires energy. Forming bonds always releases energy. So you can imagine that all values for bond energies are always going to be equal to or greater than 0. That being said, what do you do with this information? Let's use the same equation that we had last time. So the formation of water from its constituent elements. And we're going to see the formula in this case is going to be the sum of all my bonds that are being broken minus the sum of all the bonds that are being formed. Again, you'll be given a table that has information with regards to every bond. Our first step will be to identify what bonds are actually being used. All the bonds that are broken are the bonds on the left-hand side. All the bonds formed are the ones on the right-hand side. My broken bonds are H's and O's. The HH bond specifically, which will occur twice, plus the O2 bond, which is a double bond, minus all the bonds that are formed. H2O looks as follows. But there's two of these. So I have one HO bond right here, another HO bond right here. So 2 per molecule, 2 molecules, 4 HO bonds in total. Now, if we're to go back to the table, we see this OO was actually extra information. We don't need that section. We only need these three. 2 times 436 plus O double bonded is 499 minus 4 times HO. When you put this into your calculator, you get negative 481 kilojoules per mole. The change in enthalpy would be negative 481 for the formation of water. Again, this was very similar to the answer we got last time, which was negative 484, and they should be relatively close to each other because we're finding the same thing, just in a different way. Third way of finding this information is using Hess's law. Hess's law gives you a way to manipulate several changes in enthalpies given smaller steps for a reaction to make a bigger reaction. Our complete reaction in this case is N2O plus NO2 to make 3NO, and the smaller reactions are here, equations 1, 2, and 3. I'm going to call this one reaction A, B, and C. What can we do using these equations to get over here? Let's identify the three molecules. N2O, where does that show up on the left-hand side? So N2O will show up right here and only right there. Perfect. NO2, the other reactant, will show up only right here. Then 3NO, so NO, shows up on two separate sides. We know that N2O and NO2 can only come from these two. So we're going to have to use them in a certain way, and then equation 1 has to make up the difference. We need both of them on the reactant side, right? So we're going to take equation 2 and we're going to flip it around. We're going to use 2NO2 to give us 2NO plus O2. And this value will now be negative B. So B was negative 113.1. Negative B will now be positive 113.1. First rule from Hess's law, if you flip an equation, you flip the sign. In this case, we turn the equation around, so now we had to flip our sign. Second rule, if you multiply an equation by a number, you multiply the value. If I were to take this equation, multiply it by 2, I have to multiply my value by 2. And the third rule, when you add equations, you add values. So here I have negative b, but that's too much. I don't want 2NO2, I just want NO2. In that case, we are going to have to use negative b over 2, and that gives us NO2 to make NO plus 1/2 O2. Awesome. What about the next equation? We have it in the correct orientation, but again, we need to multiply it by a value. It's going to be half of that. So we're going to have N2O making N2, remember multiplying everything by 1/2, plus 1/2 O2. And this will be C over 2. We know we're going to be adding all these values, so right here, you can see these 1/2 O2s actually sum up to just give you 1 O2, which is perfect. Now, we have the last section, which is dealing with NO. Right now, I have one NO on the right-hand side. I need 3. It turns out that equation 1 has exactly what I need, 2 extra NOs. So 1 plus 2 is 3. So we're going to use that equation and that exact same orientation. N2 plus O2 gives me 2NO. This is just A. So what have I done ultimately? I have taken equation B, flipped it around, and divided by 2. Negative B over 2. We're going to add to that C over 2. And then we're going to add to that A. If you sum all these values, you get negative B over 2, so 113.1 divided by 2, plus C over 2, C is the negative value, that negative sign has to stay there, 163.2 divided by 2, plus A, which is a positive value, 180.7. When you add this up, you get approximately negative 155 kilojoules per mole. And this would be the change in enthalpy of the entire reaction.